All right. We're on 5. Slide 61. Hey folks, so let's go and get started here. We have here the Fisher projections of our sugars. You will learn to hate these or love them one way or the other, especially once you go off into biochemistry. Ooh. Okay, if you're going to go off to biochemistry. But this right here actually makes the entire isomers actually quite a bit easier to do. So remember, the Fisher projections are going to have these two ones that are going across horizontally, right, like that. Those are coming out towards you, okay? The ones that are going vertically, on the other hand, are coming away from you. They're facing away. Okay, that means that each of those crosses is actually a tetrahedral arrangement, isn't it? Towards you, away from you. Can everybody see that okay? Okay. Now, it makes it really, really easy then to arrange these and say which configuration that would be. Okay? Which enantiomer is it? Which diasteromer is it? Is it meso? All these things actually become much, much easier to do when you're in Fisher projections. Okay? And this is actually why, if you've ever looked in a health textbook, they typically put the sugars as straight chains. This is why right here. Because it's easier to draw Fisher projections of them, and rather than the closed chain, which is 90-something% of what the sugar's in. Okay? Okay, so right here we actually see some diastereomers. And can everybody see how it's a diastereomer? Because we flipped just one of those, didn't we? Yeah. Cool, huh? Okay. And so we look on the other side. Right here we have enantiomers, and see why they're enantiomers? Yeah, they're all mirror images of each other, aren't they? Or they're all flipped. Okay. Notice the D's and L's. Can everybody see that? That's that last group. The OH, the higher priority group, is on the right side, so it's a D. The higher priority group is on the left side here, and that's an L, isn't it? Okay. The identities, L's, glucose, those are actually these rotations right here. Can everybody see that okay? Yeah. All right. Now, notice that these ones right here, we stopped doing those Fisher projections. Why do we stop doing that?
Not a straight chain.
This isn't a straight chain anyways.
Okay.
Yeah. 99% of the glucose in your blood is going to be in the ring form.
Oh, right. Okay.
Yeah. But if you look at these carbons here, all of those carbons are chiral. They're all chiral carbons, aren't they? Okay. What about this one? Can that be chiral? No, it can't, because it has that double bond, right? You can't get 4 different things around it. How about this one down here? Is that chiral? No, it has the 2 hydrogens, right? And so that ends up not being chiral either. And so the asymmetric ones, the achiral ones, you don't have to put those in the Fisher projection. In fact, you don't. So that you can easily tell, hey, these are asymmetric, okay? These are not chiral. Okay, so the Fisher projections and the RS designations. Note again, we have these in a very set layout, but we have a bit of a problem with these. Is the hydrogen facing away from you or towards you? Towards you. So this is backwards, isn't it? Yeah. This is actually always backwards from what you would want to do R and S with, right? So in a Fisher projection, you always go ahead and assign them their priorities. So this is first, second, and third, right? Hydrogen being the 4th priority. You don't need to ever count the hydrogen here. You can always go, I'm going to ignore that because that would normally be behind the carbon, right? Okay, and then you go first, second, third priority. That's this direction. We would normally call that what? S. You got it. But we're backwards, aren't we? And when we do this backwards, we always need to go ahead and flip that to the other one, right? And so we're going to call this R. Okay? Anybody have any problems with that? No? Okay. Theoretically, you could also flip two items and do that way, but that's a lot of extra work, right? So as long as you understand that hydrogen's pointing out towards you, so anytime you assign the designation, you're going to always end up the opposite designation, right? Okay.
Will it tell us it's like if it's a Fisher projection, so we know to do it the opposite?
It'll look like this.
Okay.
Yeah. Yeah. Nobody writes like that. Just is such an unnatural way of writing it that you will never, ever be able to mix them up. Okay? Because like the chain is straight up and down, right, instead of left to right like it normally is. It's absolutely no zigzagging or anything, right? So it's totally unnatural way to write it. And that's very, very specific for Fisher projections. Okay? For problems for I typically do end up saying something about it and be like, take the Fisher projection and da. But you really don't need them labeled. Like nobody's ever going to write out a non-Fisher projection like that. Because it would be actually a lot harder, right? Yeah. Versus the normal way we write these things. Okay, so let's go ahead and talk about some strategies for success when we're converting back and forth between these things. Fisher projection and zigzag conformations, that is. Let's go ahead and talk about converting it to a Fisher projection first. So we go ahead and we're going to need to use the C1. C1 is going to be part of this aldehyde or carboxylic acid in this case. And the C5 is going to be part of this one right here, which is the alcohol. Neither is going to be a stereocenter. And so those are not going to be involved in the hatching or the straight up and down versus horizontal, right? For the Fisher projection. Those will be what you start with. So you can go and collapse those formulas and just write them out like this. CO2H or COOH, either way you want. Okay? And on the bottom, you can go ahead and write that out as CH2OH because they're unimportant for the Fisher projection, right? They don't have any of the stereochemistry we're looking for, do we? Okay, so the next part you're going to do is you're going to take all of these hydrogens and oxygens. You're then going to lay them out so that they are on the left or right side of each of these stereocenters. So in this case, we have 3 stereocenters. We're starting from this one here, and then that ends up going downwards, right? Okay, fantastic. So let's go ahead and talk a bit about what makes these stereocenters go on which side again. Okay. So again, this is the asymmetric carbon. If we were to do this with a 3-dimensional model and we want to work with this and write it out to a Fisher projection, what we would end up doing is we're going to take that ending that's going to be at top, and then we're going to rotate it so it would be away from us and on the top, right? Notice that is a 90-degree rotation in this case, and then another 90-degree rotation. Can everybody say that okay? Okay, fantastic. Now, what does that mean? Well, that means that these ones end up facing outwards, and this one on the left is on the left here. So as long as you get the ones facing away from you in the up and down vertical, and the ones that are facing towards you in the horizontal, it's just straight left and right. Okay. Now, this is another example right here where, again, we have to do 2 90-degree rotations. Notice, again, though, our rotations are slightly different, aren't they? Can everybody see that okay? So in the first case, we had them pointing down like this. In the next case, we had them pointing up, didn't we? Okay. Okay, so there is a way of simplifying this somewhat. So when we write this, remember that this one's going to be on top, right? Okay, fantastic. So when we rotate this, so that one's up on top, we're going to end up rotating this so it is facing towards us, right? And this is going to be the conversion. So we rotate this so it's facing towards us, like so. Everybody okay with that part so far? Okay. Okay. This one right here, the wedges are going to end up facing on the left. Right there. Okay. This one's coming out towards us. This is the next one down the chain. This one's going to be end up facing over to the right. Don't worry if you don't get it perfectly this time, because I'll have more examples where we can work through things. This one right here is going to end up facing on the right, but it faces on the right because instead of being coming out towards you, it was originally going away from you. Okay? And you see how that's an alternating pattern? Okay. Okay. That's the main connection I want to make so far. Okay, so we actually have to go the other way as well. So when we convert from a Fisher projection to a zigzag, what we would have to do is we would have to rotate it twice 90 degrees, right? So the first rotation you're going to make is you're going to go like so. So it's flat, right? And then the next rotation you have to make is you have to rotate it. Remember that these currently would be coming out towards you, right? Okay. So the next rotation you have to do is a 90 degrees this direction, which is going to make it so that one of them comes out towards you while the other is going away from you, right? Okay. Okay. So when we convert this, what we're going to do is we rotated it so the cyanide is lying flat, like so. Okay. And then we're going to rotate it the other way so that these are pointing upwards. Okay. The reason we rotate it so they're pointing upwards is because this gives us this valley right here. Because remember that this is actually like that shape, right? Okay. Okay. So when we rotate this, again, it is going to end up with an alternation. Okay? Back and forth between these. So this one was originally on the right here. That's going to be going away from us. This is one of the ways you can double check if you got things correctly, okay? This one right here is on the left, so that again is going away from us. What would this hydrogen be doing, by the way? Going towards us, yeah. And one of the ways, again, you can double check this is if they're on the same side of the Fisher projection, when you get them into zigzags, they have to alternate. Okay? Is that making sense? Okay.
So the one that's going towards you is also alternating, so that hydrogen on 2 would be going towards you, and then the hydrogen on 3.
Yes.
Those are both going towards you.
Yeah, the hydrogens are here. We just didn't bother listing them out.
Yeah.
Yeah.
Okay.
And this is one of the ways that when you rotate this, I would try to rotate this first, writing out my rotation, and then I double check it with the alternation. Okay? If you messed up your rotation and you lost track of where things are, then you won't alternate. You'll mess that up. Okay? All right, so Does anybody have any questions about this so far? It's kind of something you gotta physically actually try to do. Okay? Mm-hmm.
I'm a little confused on like going across like the hydrogen and the hydroxide. Aren't they both horizontal? So would they both be pointing towards us?
They're both horizontal, but the issue here is that it's rotating up and down. You see that? Is that making sense?
So they're still horizontal with each other?
Yeah, so they're still horizontal going in this way. Is that making more sense now?
Yes.
So like here's your carbon chain, right? And this was one carbon, this was the other. One of them's coming out towards you this way. And one's going away from you, right? And so they do end up horizontal still. But in a Fisher projection, everything was flattened, right? And in this, we have to actually account for that separation there. Does that make more sense?
Yes.
Yeah, okay. yeah, it's an artifact of us flattening it. Because if you really start thinking about these Fisher projections, I was telling you that they're going away from you, and then somehow they're going away from you on the next carbon. Which is impossible, right? Like, how the hell does that work, right? Yeah. So we're playing some games with the three-dimensional topology of these things when we do Fisher projections. And that's what's causing this to be back and forth like that. Okay? So when you actually go ahead and do it in 3 dimensions, this one right here ends up coming away from you, right? And you can do your hands if you want. It's always a good way of doing that. So like here I'm marking out my, okay. Can you guys see how I'm marking out my different locations in space? Okay. So I have my hydrogens, which are my fingers, right? I have my OH, which is my wrist. I have a slightly cupped, bent hand, right? And then my thumb is marking where I start, okay? And so what you can do is you do a 90-degree rotation, so it's this way, right? And then you do another 90-degree rotation. Can everybody see how I ended up with the hydrogen coming out towards me? And the OH going away from me. That makes sense? Okay. You can also use a model kit if you want. Okay. Okay, let's try that again. Actually, take your hand, okay? Okay, so take your hand. Okay. I'm going to use this as a 3-dimensional object so I can manipulate it, right? In case I have difficulty rotating. By the way, please don't feel bad about asking questions like this. This is an area that's a little bit difficult for me to understand where it's difficult. So like 3-dimensional topology stuff, go ahead and ask questions, please. Okay. I won't mention my IQ in it, but yeah. So if you go ahead and take your hand and make sure you cup it, your hydrogen is over here on the left side, right? Okay, and it matches up with that diagram up there. Everybody see that okay? Yeah. You can do either hand, actually. It would be the opposite.
Okay.
Yeah. So, I'm using my right hand, I know. I'm pointing different directions. I'll point towards you guys. Okay, that make a bit more sense now? Okay. Okay. And the OH is the wrist, right? Okay. So the first thing I need to do is I need to go ahead and rotate it so that top is this way, right? Okay. But I would still have both of these coming out towards me, right? And I'd still have problems actually writing that as a zigzag. Okay? So the next thing I need to do is, it actually doesn't matter which way I do this. I can go this direction or this direction. I would get the same structure overall. It would just be, one would be pointing up, one would be pointing down, right? Okay? So I'm going to go ahead because my original question was like that, right? I'm going to go ahead and rotate it so both my cups are pointing upwards. Okay? And if I remember my designations, this is the CN, right? Okay? This right here is what? Hydrogen. This one right here is OH. And so the one coming towards me being you guys, is the hydrogen, right? And I do the wedge for the hydrogen now. The one going away from me would be the OH, wouldn't it? Okay? And there we go. I've got my first one. I could do this for each of them if I wanted to double check. So I could literally go on to the next one. This would have been OH. Did everybody catch that? You can do it really fast, can't you? See that? And I'm pointing downwards this time. And so the OH going away from me again, isn't it? Okay. Everybody try that? Okay. Worked for everybody? Fantastic. This really, really is an easier way to use three-dimensional objects around you to map out these different rotations and transformations. Okay? Trying to just draw them on paper without any mapping of three-dimensional space around you is very, very difficult. Okay? Okay. Did that answer the question? Okay. Okay. And the hand actually works quite nicely, doesn't it? Yeah. By the way, there's some rules in physics that also really, really help. Okay? How'd that work for you? Didn't?
No.
Let's do it.
I don't want to do it.
I mean, okay. Really?
Which way to rotate the second time? So like you're using your hand. This is the CN.
So what I normally do here is I would go like this and sort of write out the backbone. Because that one's pretty obvious of what I'm going to have to do here. This will give me a guide to work from,
So
which is the same thing I did over here, actually. And so the first one, I'm going to line that up, and that has the CN right here. Go like that, and I need to rotate upwards, don't I? Because see, that one's upwards. The next one, I'm going to go ahead and go like this, and that's going to be going on to that carbon 2, right? Okay, and so I go ahead and rotate it this direction, just pointing towards carbon 2. My hand is carbon 3. And then that one needs to rotate cup down, right?
but isn't so that's because of the curve, like the
Yeah, that's because of the
zigzag?
zigzag. Yeah. Because in reality, instead of being, this is what this Fisher projection would look like, which is actually impossible, right? Instead, I need to account for the zigzag. Okay. Okay. You can also use pencils and pens if you'd like, but you all have different writing utensils, so that wasn't going to work for me. All right. Your hands are mostly the same? Okay.
So I get the alternating thing. So how do you know which one is dashed and which one is?
You got to get the rotation correctly on one of them. Okay? Now, part of the problem why I can't just say the one on the left is dashed. I can't say something like that. And the reason I can't say that is you could write this structure like this or like this, right? And that would flip it. So I can't tell you one or the other because you could end up flipping it on something very casual. Okay? And that's why it's better to just take something three-dimensional and manipulate it. Okay? Okay?
Oh, I think you just answered that. So if we did that same like diagram, but instead of going up first, we went down,
Exactly.
it would, you can do that, right?
So,
You just
this
turn it
step?
the other way?
Yeah.
Okay. that like after you turn it this way, if the thing goes up, that's when you turn it under like that. But
Yeah.
if it goes down, that's when you turn it.
Literally all I'm doing here is I'm just matching up the direction that these things are going to point up or down.
Got it.
And for the next one, it's going to end up pointing downwards.
That's when you do it. Got it.
Yeah.
Okay. It's
Yeah.
clean.
Yeah, I'm actually making it into something that you explored when you were a baby, right? And so you have so ingrained in you, it's instinctual. And that's what I'm trying to connect you to. Okay? Okay. What's up?
No.
No? Okay. Now, if you go ahead and do this, it's actually very, very simple. Practice it on the practice problems. What you're going to find out is you can actually do these very quickly just with your hand. And I do recommend going backwards and double checking them. Okay? Okay. Anybody have any more questions on that? Okay. Now, it is possible to just do this with your brain. That's it. It's not a common skill to be able to do. Okay? Okay. All right. Did everybody catch that it's easier if you go ahead and write this out first? Okay. Okay. All right. So let's talk about the physical and chemical properties of isomers. You may have been wondering, are these things divisible? Can you somehow separate these things? Yes. Yes, you can. They're going to have small differences in their chemical and physical properties. Sometimes these can be actually large differences. Please note that most biological systems actually have a difference between the two different conformations. Okay? So constitutional isomers with similar properties. Here we have a 1-pentene, and here we have the trans version of that for the 2-pentene. Notice the boiling points are pretty close, but not quite the same, are they? So 30 versus 37 degrees Celsius. So if you had wanted to separate these, if you were to very, very carefully distill these, you'd actually get some separation. Okay? Now, constitutional isomers that have different properties are going to have a much larger difference between these. These would be very easily to distill, wouldn't they? Yeah, you could just boil, this one would boil much, much later than this one, right? And so you'd get a very nice, easy separation. Okay? Why is that? Exactly. The hydrogen bonding, we have a hydrogen bond donor and acceptor, don't we? This one does not have a hydrogen bond donor and acceptor, right? And so it boils much easier. Okay, so the enantiomers are going to be mirror images of each other. They're going to have the same connectivity. They'll have the same polarity. Most of their chemical properties are going to be very, very similar. And their boiling points will be very, very similar as well. So how in the world do you separate those? Ooh, that seems tougher, doesn't it? Okay, but we know we can separate two things that are mirror images of each other. Can you separate your hands? Definitely can. And we have things that separate them, right? We have things like gloves, shoes, that would cause an automatic separation, don't they? Anybody ever accidentally put their left shoe on the right? It's okay if you say it. Don't be embarrassed. It happens. That just means you've been busy in life. Okay? And it's unpleasant, isn't it? Yeah. So, again, these are going to have essentially identical properties. Okay? Typically, their physical and chemical properties are identical for most cases. Okay? There's a plane of symmetry. So in an achiral environment, enantiomers are going to have the exact same physical and chemical properties. In a chiral environment, the enantiomers are going to have different physical and chemical properties. So if you are in an environment where it's achiral, for example, you have single set socks, like almost all of us have, right? There's no difference between our right and left sock. it doesn't matter which one you attach to which foot, right? And so there is no separating property, okay? But what happens when we start using something chiral to attach to it? What happens when we make the gloves chiral? A right-handed glove and a left-handed glove. Can you put your right hand in your left-handed glove? That don't work out, does it? Yeah. And so suddenly we get the ability to separate the chiral constituents when the environment is chiral. Okay? So diastomers must have different physical and chemical properties. You can actually see this pretty nicely right here. This is the cis and trans. And we see if we have chlorines or chlorides on both sides, what we end up getting, one of them has them on the same side of that double bond, don't they? See that? And so we're overall polar, aren't we? If we were to put those things together, they'd be dipole-dipole interactions, and they'd boil at a higher temperature, wouldn't they? This right here, on the other hand, because the chlorines are on different sides, they actually end up being nonpolar. They cancel out the overall molecular dipole, don't they? And this actually makes it boil much faster. And so we can actually separate these diastomers just by boiling. Okay? Just a nice, easy distillation. This one right here actually has pretty similar properties, but not quite. Okay? They're within like 1-2 degrees of each other depending on what you're doing with them. Okay? Depending on the conditions. So you see that this is like 3 degrees difference for the sweating, 2 degrees difference for the fusion, right? Probably not going to be able to tell the difference between those, are you? Okay? If you tried to distill these separate, it's unlikely you get any real separation at all. Okay? So they have very similar properties. So let's go ahead and look at separating configurational isomers. Louis Pasteur was actually the first to isolate a pair of enantiomers from each other. Pasteur noted that the crystals appear to grow in one of two varieties. There was a left-handed orientation crystal and a right-handed orientation crystal. And they are mirror images of each other. Can everybody see that crystal's different? Mirror images, they're enantiomers. Okay, so you take a microscope, pair of tweezers, very carefully remove one layer from the other. They're visibly different, right? So you can physically remove those. And that was actually a separation of two different enantiomers. One was a left-handed crystal, and it was that way because it was a left-handed enantiomer, if you will. Okay. The other on the hand was right-handed crystal because it had an orientation that was right-handed when it bound together. Okay. Okay. Now, how about an alternate method for separating enantiomers? Not everything's going to be nice crystals that you can separate layers, right? And probably nobody wants to take a microscope and tweezers anyways. I imagine that probably isn't something you particularly feel like doing. So, one, you can temporarily convert the enantiomers into a pair of diastomers. This will now have different physical properties, and so you can separate them using the normal sorts of physical property separations you've normally done. For example, you can do a crystallization as solvent, you could do a distillation, any of those would work, depending on what diastomers you end up with. Okay? You can separate those diastomers from each other by exploiting their different physical and chemical properties, of course. You can regenerate then the enantiomers from your separated diastomers. The chiral molecules interact with the plane of polarized light. When all photons from light sources have their electric fields oscillating in the same plane, then the light is plane polarized. This is actually how we can tell the difference between two different enantiomers. Okay? So you may have noticed that we have these higher priority groups, right? Why were we always going higher priority groups, larger atomic numbers, then mass after that? Well, that's actually because those are going to change how things polarize light. Has everybody used their phone with sunglasses on? Yeah? Or seen two sunglasses where you're like manipulating them against each other? Okay. Okay, that's actually polarized light. That's actually what sunglasses do. They don't let one plane of polarization through as much as the other. And so it darkens it. Okay? And this is actually what we're going to be taking advantage of. When light passes through something that has a rotation to it that's in one direction, it's actually going to rotate the light so it's more coherent in one direction. And then what we're going to get is a change in that rotation. Okay? Think of it a bit like this. If I had something come to my hand and then I passed my hand off, right? Okay. If it came into my hand at an angle, what would happen? I'd tilt it in a certain direction and then I pass it off in that certain direction, right? Okay. The same thing's going to happen when you have chirality to these molecules. Okay. Okay. And so right here, this is actually how the magnetic field versus the electric field is separated. Has everybody seen that before? In one way or another? No? Okay. Okay. So the electric fields are going to oscillate in your same plane. The light is then going to polarize in a induced plane, if that makes sense. Okay. Have you guys taken physics 2, by the way? No? Okay, that's fair. That's fair. Okay. Anybody ever worked with electricity at all? No? Okay. Okay, that's okay. Everybody's familiar with the fact that the magnetic field around a wire changes, right? No? Never seen electromagnets or anything? Okay, okay. Fair enough. We won't get any more depth into that. We're just gonna, if you're curious, we can talk about it sometime. But understand that when you're talking about magnetic fields and electricity, or you're talking about magnetic fields and electric fields, like electromagnetic radiation, i.e. light, they're actually at a perpendicular to each other. Okay? And there's some pretty interesting things you can do with that and factoids that gives you. For example, the power from an electrical circuit does not actually run along the wire. The power that does stuff actually runs in the electromagnetic field around it. Okay? And there's some kind of interesting stuff, like how fast a circuit would respond, that changes because of that. Okay? Anyways, a little note here. Who here has taken some biology where you talked about enzymes? Okay. And did you guys talk anything about the DL forms of these different substrates can be used or can't be used? No? Yeah? Okay, so I'm going to put something in your head that you can go ahead and have for that stuff, okay? And that's another way to separate enantiomers. Is because if you have something that has chirality to it, and it binds to something that is chiral, it's going to change depending on what you're binding. For example, has anybody ever tried to, everybody's shaken somebody's hand, right? Right hand to right hand, shake. Anybody ever tried to do that where the person doesn't have a right hand, free, or they don't have a right hand? Okay? Yeah, and you got to flip, and it's awkward and weird, and obviously that doesn't bind as well, right? Yeah. And so that's actually why enzymes, which are chiral, can separate substrates, which are chiral, from each other. Okay? And that's one of the methods that's actually more used than this method now. They used to do reactions and convert it, but we have a wide variety of different binding chiral compounds now for most of the stuff you'll want to work with that you can use to do these separations. They're based on enzymes loosely, usually. Sometimes they're not, but yeah. So I'm just putting that out there. You'll see that in biochem. You'll talk a little bit about that probably. Yeah. So let's talk about the polarizer. So one of the ways we can determine which of these chiral compounds we have, or if we have more of one than the other, is that we can use a polarized source of light. Now, most light sources will actually emit light that's unpolarized, okay? And that's why you can see them when you're wearing sunglasses, okay? Has anybody tried to check their phone, though, when they have sunglasses on? No? You don't have any sunglasses? Clip-ons? No? So, like, at certain angles, your phone's really hard to see, right? And, like, the screen basically disappears. Okay?
Maybe mine just suck. I can see everything.
Tilt it this way. Uh,
I don't have one of those like privacy protectors.
that's unusual. So typically, we can play with it later. You can actually just rotate the glasses over the phone, and you'll be able to see it. But we'll play with it later, or you can do it now, either way. And your computer screen should actually do the same thing as well. And that's because LEDs actually put out light in a polarized manner. Not perfectly, but pretty close. Okay? Anyways, traditional light sources did not. And so what you can use is what's called a polarizer. It's going to generate a plane polarized light. It'll filter out all the light whose electric field oscillates in any other plane than the one you want to go through. This is actually very, very common for almost any type of spectroscopy or detection methods. Sunglasses are polarizers, but you can actually make a polarizer just by cutting slits very carefully. Okay? That's actually why, for example, has anybody seen those like old welding goggles or sunglasses that have like the slots? Yeah, that's what that is. It's the slits are causing the polarization. Anyways, and so when it came into your eye, it would be polarized. Now, if you do this before a sample, and that sample is chiral, what's going to happen is that sample will actually rotate the light in one given direction. And so the angle a chiral compound rotates plane polarized light, this is actually called the measured angle of rotation. It's given a symbol alpha. And yes, chemists have absolutely no naming imagination at all, which is actually really great when you're learning it, right? Literally, the angle of rotation, right? We're measuring an angle of rotation. Okay. So light is going to enter the analyzer, if you will. After it exits the sample, so we polarized it right here, and then we enter the sample right here, right? And then it goes over here, and this is what we call the analyzer. Okay? Guess what that analyzer is? Just another polarizer. You got it. Yeah. So you literally line the two polarizers up, and that tells you the rotation. Okay? So if there was no rotation, these polarizers would be the exact same angle, right? If there is rotation, then your front one here in front of your eye is going to rotate off of that. Okay? And that will be your brightest point. That will be your brightest vision of this. Your detector in these cases, you can use automated detectors, and basically they're like the camera in your cell phone, but oftentimes it's just your eye, because you're actually pretty good at this. Okay? So you can just use your eye, and that's your detector. Anybody ever heard of Raman from Raman Spectroscopy, won the Nobel Prize? Okay, then it's a terrible story, and it's not going to work. That person won the Nobel Prize on a double-spaced paper that had margins about 2 inches, one page. And he used the sun as the source of light and his eyes as the detector. Yep. Okay, now he did a bunch of work later, but that was his seminal work. Yeah. Groundbreaking work. So the factors that govern the angle of rotation, these are going to be things like the concentration. So the chiral compound increases as its concentration increases. So does the angle of rotation. You can think of it a bit like if I have one hand rotating things, there's only so much rotation I can do, right? If I have many hands rotating things, there's a lot more rotation I can do, right? As the length of your sample tube increases, so does the angle of rotation. So that right there is the length. That's the concentration right there. That's the measured angle of rotation right there. And this one with the brackets is the specific rotation. That one's the constant. That's going to be unique for a given chiral compound. That one comes from the priorities of group and how priorities they are, how large they are, and at what angles they would be. Basically, it's how much that weight of those molecules and the electric fields of them messes with the light. Okay? Or your strength of your hands, right? Okay. Okay, so enantiomers. If you have an enantiomer of something, those are always mirror images, right? And so an enantiomer is always going to have the equal magnitude, but the exact opposite sign for this constant. Okay? And again, that's because they're going to be the same, but in the opposite direction, right? Same, but mirror image. Okay. Okay, now note that the one weird thing about this is the concentration is going to be in grams per milliliter. That's not that weird, is it? Those are things that you can measure very easily in lab. Makes sense, right? Yes, that does mean that concentration, density, always was a concentration, wasn't it? Yeah. Yeah, density was always a concentration. We tricked you. The length is actually going to be in decimeters, which is weird, isn't it? Can anybody tell me why that would be in decimeters? They're not very small. They're actually bigger than centimeters, right?
Are they?
They are. Yeah, deci meaning decimal. So they're a tenth of a liter. Okay? Decimeter, partially it's like that because these tubes are oftentimes in decimeter sizes. The other part of that is actually that the decimeters matches up nicely to the centimeter cubed, which is the milliliter, right? Okay. So racemic mixture. This is going to contain equal amounts of the plus and minus enantiomers. What do you think the plus and minus means, by the way?
It's the flipped
Yeah.
to each other.
Yeah, remember we're rotating this off of a central point. And so if we go one direction, that's going to be positive rotation, let's say 30 degrees, right? If we go the other direction, that's going to be negative rotation. Again, 30 degrees if we have enantiomers, right? Okay. All right, so racemic mixture of enantiomers is going to actually be optically inactive. Again, this is going to be despite the fact that it's two different chiral molecules. Why would it be optically inactive? Let's say I have one thing that rotates by 30 degrees on the right, the clockwise. And I have another thing, equal amounts, that's rotating it 30 degrees the other way. What's going to happen? Yeah, I rotated 30 degrees one way, back. And so each of them just keeps rotating it right back. I get no overall rotation, right? Yeah, don't accomplish anything. And so that's what a racemic mixture is. It's a mixture of the two different enantiomers. That's 50-50. Okay? 50% of each. If a mixture of enantiomers is not racemic, then it's going to be optically active. What does that mean if it's not racemic? Does it mean I have all of one? Yeah, I literally just have a little bit more in the other. That's fine. I could have almost all of one. That would also be non-racemic, right? Or not racemic. Okay, so the excess percentage that favors one enantiomer is going to be what's called the enantiomeric excess, abbreviated EE. This is going to be calculated. We'll use this equation right here. And so this is going to be the percent EE, enantiomeric excess, times the specific rotation of a pure enantiomer. This is then divided by 100, and that's actually what would equal then that rotation that you got from the mixture. Okay? So that would give you the specific rotation of the mixture. This is oftentimes what we would actually have. And so we would typically solve for this side right here. Okay? However, I can give you practice problems going anyway, right? Test your ability to solve any direction in an equation. Oh my goodness. Okay, so let's talk about the chirality of biomolecules. This one is a chiral biomolecule. It's oftentimes sold as a racemic mixture of its two enantiomers, and this is actually where we see the enantiomers. This enantiomer right here suppresses nausea. This enantiomer, on the other hand, causes birth defects. Pretty common, actually.
Wasn't there a case where there was like the drugs that were suppressing nausea were being given to women, but there was the wrong.
Yeah. Oh, yeah.
That was
It happens.
lawsuit?
Yeah. Yeah, it happens. And I'm sure that there's been other times that they've done that, or they did not have a very purified sample, and nobody ever found out. I'm absolutely certain. Yeah, it's especially if you get. So this is one of those places where like it's very expensive to check and separate these enantiomers. That adds a lot of cost because you have to actually have somebody fairly competent that's checking these things, right? And you have to get rid of or purify these samples if they're wrong. And so this is one of those areas where if you start buying things from countries where they don't make them do that and they don't have strong reporting requirements, Mexico used to be a really bad example of it, but it's less so as long as you don't buy from the unofficial markets and go down there. Yeah. But there's other countries that have been really bad examples right now. I don't really want to. Yeah. But so this is one of those areas that reporting requirements really become incredibly important. And your typical like U.S. sold drug becomes really expensive because it has a series of checks and balances that somebody is checking this all along the way and making sure. But even then, sometimes the supply lines get messed up. And it happens. This is not the only case of this, by the way. Most of the cases are somewhat benign. And so people buy like protein powders. They get 50-50 mixtures. One of them they can't use and they just end up excreting it. That's why a lot of these protein powders and stuff have large amounts of like fiber. Because it's junk they're selling you that you can't use, right? So, fiber. On the other hand, though, you can get things like the caraway is always interesting. The other enantiomer is a totally different flavor. But you can also get things where one of them is a medicine like this. The other is what we would consider a poison, right? And there are actually more extreme examples of this where you can kill people. Probably the funniest, though, is the University of Iowa had somebody busted for making meth. They stole a bunch of equipment from the lab up there. And so they made meth, and then they made the wrong enantiomer of meth. And at the time, the law was such that if you made the wrong enantiomer does not have any properties. When you take it, it doesn't do anything. You don't get high. So that was not actually illegal. So the person actually managed to, through their own incompetence, avoid going to jail. Yeah. Got thrown out of the university for stealing, but yes. Avoided going to jail. That's the Breaking Bad Walter White, by the way. That's why his meth was special and you got better high and stuff. Is because it is anatomically pure. Yeah. Yeah. But anyways, yeah. Everybody always asks me about the Breaking Bad stuff, so. But yeah, you are exactly right. This like happens on a fairly regular basis. And for most of these things, it's the drug does not end up being as active. And you don't get as much effect as you should. But every now and then, something horrific like that happens. And yeah. Yes. And nausea drugs are not uncommon to give pregnant women, right? At all. So, yeah. Horrific. Anyways, let's try to move on from that, which that was a deep and dark hole that we went into. So, again, this is nausea drug, of course. I think we pretty much covered that. So this is some different chiral centers and biomolecules. Here we have the amino acids, of course, and this is why you can see the amino acids being sold in like health supplement stores. And if you ever go to the better amino acids that are being sold, there'll be like D or L, and they'll actually have at least an attempt to purify. And it will actually tell you it's 90% this or 70% or whatever. Okay. Here's glucose. We normally don't actually spend a lot of time trying to purify the glucose, but it would matter actually. Yeah, the chirality does matter. This right here is a nucleotide in DNA, and again, it has numerous chiral centers. And yes, if you had the wrong chirality for your DNA, it would not function. And that would be a problem. Right here's testosterone, of course. Okay, so the basis for the DL system is actually the optical rotation of glyceraldehyde. So if you had ever wondered where in the world does this DL stuff come in, we had the RS system. Why does he keep talking about biological compounds that are DNL? Why have I heard of D-glucose, L-glucose, that sort of thing? Okay, this is where it comes in. It's just a more direct way of labeling the two, because you can experimentally observe it. Okay? So some of the D sugars are going to rotate plane polarized light in the clockwise direction. Other are going to rotate in the counterclockwise direction. Some of the L sugars are going to rotate the plane polarized light in the clockwise direction, and others rotate in the counterclockwise direction. The DL system was set for glyceraldehyde because that rotated it in the DL clockwise, counterclockwise. Okay? The other sugars were set from the last group being on the right side or left side. Okay? So it doesn't necessarily correspond for the other sugars. So D-glyceraldehyde actually is going to rotate the plane polarized right in the clockwise direction. This is actually referred to as dextrorotary. That's where the D comes from. Okay? The D sugars other than glyceraldehyde could be anything. All it means for the other sugars is that last OH is on the right side, which matches up with glyceraldehyde. Okay? The L-glyceraldehyde is going to rotate the plane polarized right in the counterclockwise direction. This is levorotary. And again, for the other sugars, it doesn't match up because they just wanted the last OH to match glyceraldehyde. All right, so these are the amino acids. It's actually rotation around this bond right here that determines that D or L. And so this is the D-glyceraldehyde, and right here we have the D-amino acid. And so we take this group right here as being analogous to the CH2OH group, and this group right here is then analogous to the OH right there. Okay? And that's how you get the D and L on the amino acids. I know. It's a historical system that I feel that they probably really botched. But
I don't see like a rotation. What does it mean? Like,
So it's the rotation, like this could be coming towards you, but this one could also be coming away from you. And that would give you the two different chiralities.
Oh, okay.
Okay?
So it's
We're
like-
still talking RS. This is just a new terminology for it.
Okay.
Okay? Mm-hmm.
Is D wedged and the other one just dashed, or?
Yeah, so the D is the wedged. If you had the other one, it would be the dashed.
Oh,
Yeah.
okay.
Yeah, that's the L right here.
Is it always like that, or?
For the amino acids, yeah. These two groups are consistent across the amino acids. The only one that changes in amino acids is the R group. And yeah. Now it is set like that, not because that's going to give a right-handed rotation of the clockwise rotation of the light. It's set that way because it's analogous to the glyceraldehyde, which is kind of stupid, but it's what it is. Yeah. I probably would not have done it. I would have been very experimental with it if I was going to do it. And whatever direction the light rotated, that would be D and L. But then your sugars would have all been different, right? You wouldn't have been able to go, the last OH is D, that's D. So, I don't know. I can't really say much about that, right? But, yes, so did the amino acid make sense?
Yes.
Okay. So if we look at the sugars here, these are the sugar families. And so what you see here is the D just denotes this last OH. Okay? So if the last OH on the sugar in the Fisher projection is on the right, that's a D. If the last sugar on the Fisher projection is on the left, that's an L. Okay? The erythros, threose, glucose, mannose, all that stuff, that's set by all of this. Is there a rotation? Like, is the OH on the right on this one, then on the left, and the right, right. And then you'd get the other enantiomer, the L enantiomer, by swapping all of those over. Okay? Okay. Do I still have everybody with me? Yeah? Just remember that the D and L here, just the last one right here.
And you said if it's on the right side, it's D. If it's on the left side, it's L.
Mm-hmm. Yeah. See how all of these are on the right side? Yeah. Yeah, these are all the Ds. Yeah. The name comes from these being on which side. So like a glucose would be, a D-glucose would be this right here. And then if you wanted L-glucose, you just swap all the hydrogens and OHs. Okay. Okay, so that's a D and L-glucose, and you can see that you just swap all the hydrogens. See that? They're just mirror images of each other. Because again, that's what we're talking about ultimately. We're talking about the enantiomers of each other, meaning that mirror images, right? Yeah. Okay. No. I hate the DNL terminology, but honestly, I get it. I entirely get why they did it. Can everybody understand why they did that? So let's say they had not done that and they had done it experimentally. What would have happened if they had done this experimentally instead is these have different light rotations. Basically all of them. Okay? And so you would have had no way of looking at a sugar structure and actually predicting D or L and naming it. It would have had to be, you get the sugar, you look at it under a polarimeter, which is what this is called, and you determine experimentally what it is. And all the biochemistry people would have just been shit out of luck. And they would have been sitting here like, I don't know, is that D or L? I have no idea. Okay? Because I don't have time to go in the lab and test 20 sugars. Right? Yeah.
Is it that last OH that like what's so important about the last OH? Why do they pick that one?
Because this one has one OH. They could have picked the first and last,
Yeah.
and they picked the last.
Okay.
Yeah.
So then it just stays with that.
Yeah.
one.
Yeah, it just stays the last OH. This is always the aldehyde or ketone up here. Yep, and the last one down here is always that CH2OH. And they just match the CH2OH here and called that the matching one. And I don't know this for a fact, but I'm 90% sure that they did that because this top group here can have aldehydes and ketones. So they don't always match perfectly. Yeah. So they took the one that always matches perfectly. Yeah. Which is the last one. I know, it's kind of silly, a little bit arbitrary, but it works. Okay, anybody have any questions about that? No? Okay. What's my time look like?